Hi, my name is Rafael and I'm a PhD student at the University of São Paulo. Today I would like to present this paper entitled Multi-Objective Optimization of Hydrogen and Electricity Cogeneration using Solid Oxide Fuel Cells and Biogas for this CPOTE conference. My co-author is Professor Silvio Oliveira Jr., which is also my PhD supervisor. In this presentation, we will explain the motivations for this work and show some highlights of this research, such as the optimization results and the trade-offs of some design options. In order to understand the motivations of this work, we should ask ourselves how we can reduce greenhouse gas emissions. As it can be seen in this chart, agriculture, transportation, energy conversion, and wastes are main sources of carbon dioxide equivalent emissions. These emissions could be reduced by treating and converting wastes from agriculture into energy and biofuels. This option could also improve the efficiency of existing processes in our economy. In the current context, the distributed generation using biogas has been growing in the last few years, and the majority of biogas plants have an installed capacity lower than 100 kilowatts. The development of efficient systems for distributed generation using biogas could promote great benefits for society and the environment. This leads us to the objective of this research. Which improvements can we propose in this field? Our research aims to optimize the production of hydrogen and electricity from biogas using fuel cells. This could increase the efficiency of small biogas plants and provide a clean source of hydrogen. Although these systems may be similar to those using natural gas or just producing power, the optimal conditions may be quite different due to the composition of biogas and the scale of power generation. In order to exemplify how different these systems may behave, the optimization routine was also performed in a system only producing electricity. This comparison may explain if the hydrogen production promotes real benefits, which are the difference between these two systems. And how did we solve these questions? The system optimized in this study consists in a sequence of calculations, which consist in a thermodynamic model, a linear optimization to minimize the consumption of external heat, a mixed integer optimization to compute a feasible heat exchanger network with a minimal number of units, and the objective functions of net present value and energy efficiency. The design variables for these functions are optimized using a multi-objective optimization algorithm, the NASGA-2. Once this top criteria is attained, the set of design variables with best results are obtained. In this study, 4 design variables for the fuel cell were optimized. These variables were chosen based on the parametric analysis from a previous study. This procedure is fairly similar to other methodologies proposed by previous researchers, but it differs in the approach to estimate the heat exchanger network cost. In this research, the heat transfer rate and the string pairs for each heat exchanger unit are determined by an optimization procedure. In theory, this method conveys better cost estimations for the heat exchanger network. The thermodynamic model was developed using the Julia programming language in order to minimize the computation time necessary to solve the solid oxide fuel cell model. The electrochemical model for the fuel cell was calibrated using data of experimental results in the literature. Furthermore, in order to estimate the influence of temperature and composition variation along the fuel cells, the model used in this research is quasi-two-dimensional. A detailed explanation of the model and its assumptions are given in the conference paper. Based on these methods, we were able to determine optimal solutions for the proposed scenarios and design variables. In this figure, each mark represents an optimal system which is located based on its energy efficiency and its net present value. As it can be observed, the co-production of hydrogen and electricity achieves higher values in both of the two functions. For instance, the net present value for the hydrogen and electricity cogeneration is at least 2.4 times higher than the power generation case. On the other hand, the difference in energy efficiency are 17% at maximum. These results can be mainly attributed to the higher efficiency of hydrogen production compared with power generation at elevated fuel use ratios, in which there are huge losses caused by the low concentration of fuel. Furthermore, the specific cost of hydrogen is assumed to be 20% higher than electricity, which favors the expected revenues of hydrogen production. If we analyze the extreme case for each scenario, maximum efficiency and net present value, it is possible to understand the influence of design variables in the system. For instance, an increase in current density is able to decrease the stack's size, and consequently it costs, but it also reduces the efficiency of power conversion. Thus, a low current density would favor higher efficiencies, while a high current density may benefit revenues. On the other hand, the fuel use ratio for solar power generation is quite high, since this prevents losses and increases the amount of power generation. However, in the hydrogen production scenario, the fuel use ratio is quite low. This is because the fuel not converted in the fuel cell can be recovered in the hydrogen separation. The other differences in temperature and air ratio can be explained by analyzing the internal reforming of methane. This reaction is favored by high temperatures and affects the amount of hydrogen available for separation. Thus, in cases with hydrogen production, the inlet temperature and air ratio tend to be higher. However, there is a trade-off since these variables also affect the costs for the heat exchanger network. At last, we can also analyze the difference in capital investment of the two scenarios. The breakdown of equipment costs for cases with maximum net present value are shown in this figure. Since the fuel use ratio is reduced with hydrogen production, the fuel cell size and costs can be greatly reduced. This allows the hydrogen cogeneration system to maintain an investment cost similar to power generation systems, since the additional equipment cost is counterbalanced by the reduction in fuel cell cost. Another great difference is in the heat exchanger network cost. Since less fuel is burned due to hydrogen production, there is less heat available at high temperatures compared to the power generation case, and consequently lower temperature differences, which leads to more heat transfer area and cost. And with these results, we can summarize the main highlights of this research. In this study, a multi-objective optimization of biogas conversion system co-producing hydrogen and power using solid oxide fuel cells is proposed, and analyzed in comparison with a power generation system. The results indicate that the cogeneration of hydrogen and power can drastically increase the net present value of the project and improve the energy efficiency with a slight higher investment cost. Although the electrochemical conversion of fuel cells is quite efficient, the process efficiency is penalized at high fuel use ratios by the lower concentration of fuel. Thus, the hydrogen enrichment and separation of the anode outlet gas can be an alternative to achieve higher efficiencies. The hydrogen cogeneration system is also able to maintain investment costs similar to power generation systems, since the additional equipment cost is counterbalanced by the reduction in fuel cell costs. And with this, I finish my presentation. I would like to thank you all for your attention, and if you have any questions or comments, please send it to me via email. Thank you very much.